So a third type of notation you could use here, actually, I don't need anything right here. Instead of calling this y prime, you might see it written as dy dx. That would be your first derivative. For the second derivative, it was d squared y over dx squared. And this would just continue on. If you're doing a third derivative, it'd be d cubed y over dx cubed. If you wanted a seventh derivative, it would be d to the seventh y over dx to the seventh. So that's just notation for asking for this.
So I understand that your first derivative gives you instantaneous rate of change, which would be the rate of change of the rate of change, right?
The second derivative is the rate of change of the rate of change.
Okay.
Yeah.
So
that's like acceleration.
Okay. So after that, what's the practical use?
I think after that you're probably getting beyond my level of understanding. I do know that the third derivative has some sort of application in physics, and it's called the jerk. And the only reason I know this is because I like math T-shirts, and there's a lot of math T-shirts that say don't be a d cubed y over dy cubed, because that is.
You have it?
I do not, because I don't understand what a jerk is, so I don't like to wear T-shirts if I don't understand what they're talking about. So somebody might ask me, and then I'll look dumb. So I just know that it is called the jerk. But if I ever go learn more about the jerk and what it is, I will maybe get me a T-shirt for it, because it's a good T-shirt if you know what it is. But beyond, I do know that has a name as far as like its application. I'm not certain. Beyond that, I'm not sure. It might. I'm sure somebody somewhere can use it for something, but I just don't. It's probably way on up there for that. Okay. All right. So notation-wise, this is what we've got. So here is our first example. We're finding the second derivative for f of x equals 6x squared minus 3x plus 2. And so higher order derivatives, you're just finding the derivative 2 times, right? That's all you're doing. And so if you have a problem like this, it is going to be pretty simple, because the first derivative is just a power rule problem. So for that web, what do we get? Very good. And then, Ethan, what do we get for the second derivative?
12.
Just 12.
You're like a smooth way to say the second or the third derivative. You know, the first one be y prime. Is there a word for that?
You would say, like, you can call it y double prime or y triple prime if it's, yeah. So, or it's f prime, f double prime, f triple prime, and so on. So, and if we kept going, what would the third derivative be for this one? Be 0. What's the fourth derivative? 0. All successive, after you get to the third derivative, everything's going to be 0 from there on out.
For every derivative?
For this type of derivative. Once you get to 0, it's going to be 0 forever. It's not the case for all derivatives, though. So if we look at this next one. We got y equals the square root of x plus 2. And we are supposed to find the second derivative such that x equals 2. Whenever asked for something like this, like second derivative such that x equals 2, you can't plug the 2 in until you've gotten all the way to the second derivative. So don't try to plug it in right away. Okay, so in order to find the second derivative, you must first find the first derivative. And I'm going to think about this as x plus 2 to the 1/2 there. And so the first derivative is going to equal 1/2 x plus 2 to the negative 1/2. I would multiply by the derivative of the inside, but what is the derivative of the inside? 1, so it's not going to change anything. And so if I want to take the derivative again, I'm just going to do the second derivative is going to equal, now I'll get negative 1/4 x plus 2 to the negative 3/2. Negative 1/2 minus 1 will give us negative 3/2. And again, I'm multiplying by the derivative of the inside part, but what is it? Just 1, so I don't have to do any. I don't have to write that part. Okay, so once we have got this, we want to plug in the x equals 2, so the second derivative such that x equals 2 is going to give me negative 1/4 times 4. I'm doing that in my head. Let me plug it in. 2 plus 2 times to the negative 3/2. And so I've got negative 1/4 times 4 to the negative 3/2. Okay, 4 to the negative 3/2. What should we do with that? Is the square root of 4 cubed, but it's in the bottom of the fraction because it's a negative exponent. So like to do it a step at a time so we don't confuse ourselves, I would move it back down to the bottom, which would give me 4 times 4 to the 3/2. And then I could write that as a root. It is the square root of 4 to the 3rd. And so I was talking about this the other day. We can do 4 to the 3rd and take the square root of that. It's not that difficult to do, but sometimes you get bigger numbers where it is pretty difficult to do. Another way of thinking about the square root of 4 to the 3rd is it can also be written as the square root of 4 to the 3rd. Okay? And what is the square root of 4? 2. 2 to the 3rd would be 8. So what we've got here is negative 1 over 4 times 8. So we get negative 1 over 32. Okay, everybody okay here? Okay. Now that, I need to give you, yeah, we do need to do that one, but I might add one more on here after this one. Let's do this one first. We've really already done these because we did some implicit differentiation problems already. We've got if x squared plus y squared equals 64. We're specifying the second derivative in terms of x and y, which means we can't leave a dy dx in our answer. We got to replace it. So in order to find second derivative, we must first find the first derivative. So for this one, we'll get 2x plus 2y dy dx equals 0. And so we will move that 2x to the other side, 2y dy dx. equals negative 2x. We'll divide by 2y. And dy dx will equal just negative x over y. For the sake of doing that second derivative, it might be easier to pick either the numerator or denominator to put that negative in. I'm going to call it negative x over y. That would be the same. So for my second derivative, I've got to use the quotient rule. So I will have y times the derivative of negative x, which will be negative 1, minus negative x times the derivative of y, which is dy over dx, over y squared. So to clean that up a little bit, I'm going to have negative y plus x dy dx over y squared. Do you guys remember what to do next? Plug in negative x over y for our dy dx. So I've got negative y plus x times negative x over y over y squared. And so if I put those two right there together, I've got negative y minus x squared over y times y squared. And it is unlikely that they'll leave that as a complex fraction. So what could I do to get rid of the complex fraction? Multiply the bottom and the top by y. And so if I do that, I will get negative y squared when I distribute here. And then when I distribute here, I will get minus x squared over y to the third. However, this particular problem, the back of the book or the answer choices, are probably not going to leave it like that. They are probably, back up here, going to give you an answer of negative 64 over y to the third. Because what does 64 equal? X squared plus y squared. This is not x squared plus y squared, but all we have to do is factor out a negative 1, and then we could have x squared plus y squared here. And x squared plus y squared can be plugged in right there for that 64, and we'll get negative 64 over y to the third. That last little step is why a multiple choice problem can actually be way harder than a free response problem. Because if you had a free response question, you could leave your answer, even if you need to simplify it to use it later, you could leave your answer here, or even really free response, you can leave it on FRQ, you could leave it here. Right? You would, if you didn't need it for anything else, you could leave the complex fraction, it would be fine. But by making this multiple choice and making that negative 64 over y cubed, they add like a whole other element to the problem that makes it pretty tough. So watch out for that tomorrow. Like if you are doing a problem like one from the warm-up or one like this, and you're like, I did this right. I know I did it right, and my answer choices don't even look anything like what I started with. Look back at the original problem and look for something you might could substitute in, because it's not a trick they're going to do often, but it is. I do see it, on those problems. problem. So it's not like I'm going to do this on 5 different questions on Monday's test, but it might show up on a few. Okay, I do want to add one more question here. Let's do an example 4, and let's say if f of x equals cosine of negative 3x, find f triple prime of, let's just go f triple prime of x. Okay. Third derivative means you got to take the derivative 3 times. They won't give that to you on like a big quotient product rule kind of question where you've got to just like, where it would take half a day to do it. But on a problem like this, you definitely might see it because these are quick derivatives. They're also never going to be 0. They're just going to keep on going. So f prime of x, what's the derivative of cosine? It is negative sine of, keep the stuff on the inside the same, but what do I have to multiply that by? Negative 3. So if we clean that up a little bit, we get 3 sine of negative 3x. That's our first derivative. So if we go to take the derivative of this again, we got our 3. What's the derivative of sine? Cosine of, keep the stuff on the inside the same, but what have I got to multiply it by? Negative 3. So I've got f double prime of x is going to equal negative 9 cosine of 3x. Okay? Oh, yes. Thanks. Then, my third derivative here, I've got the negative 9 is just a coefficient, so I can leave it like it is. What's the derivative of cosine? Negative sine. And I must multiply that by the derivative of the inside, which is, again, negative 3. And so for that one, I will get my f triple prime of x is negative 27, right? Because I got negative 9 times negative 3, but I also have this negative right here, so that's going to be negative 27 sine of negative 3x. So trig is one that they will give you repetitively. Let's see, should I add a couple? Might just add a couple more problems instead of doing an assignment on this one, because we got to start on our review. What's that? I'm going to add these 2 more. Let's do a couple other types of problems that they will often give you like higher derivatives of are, let's see, this is example 5. If f of x equals natural log of 4x, find, let's do f triple prime of x, and the other type you'll see pretty often, if f of x equals e to the 3x, find, let's do the 4th derivative of that one. Okay, try those 2 on your own. I'll freeze my screen so you can't see my work. Do you have to use quotient rule on number 5?
Probably not.
Your life will be so much easier if you do not.
It's not very difficult.
It's not a super difficult quotient rule, but what is 1 over x? How else could you write it? X to the negative 1, and it will be much easier. Positive 2x to the negative third. They might leave it like this. They might move that x to the third back down to the denominator. Either one of these answers right here is fine. Mm-hmm. Yeah. You can do it with quotient rule, but it's just much easier. Yeah. Okay. For f of x equals e to the 3x, e is the easiest thing we can take the derivative of because it is itself, but you do have to use a chain rule for this. So you would do the derivative of e to the 3x is e to the 3x. It just stays the same, but you must multiply by the derivative of 3x, which is 3. So you get 3e to the 3x for your first derivative. Well, you got to do the same thing again. Basically, you just keep multiplying by 3, right? So this next one is 9e to the 3x. Then you got 27e to the 3x. And last you should get 81e to the 3x. So that one's a really easy one for them to ask you a really high derivative on. Especially if they use like 3x or 2x, they could ask you the 4th, 5th, 6th derivative. And it is not very difficult to compute there. So natural logs, e's, and trig, you might see those asked for like 3rd, 4th, 5th derivative. You will probably not see it if it's just like a regular x and y type of situation, unless it's like that very first problem we did where it's a really easy one to take the derivative of. Okay, so we are not